Welcome back. In this video I'm going to be explaining about quantification of numerical error using the Taylor series. So if you remember back from our previous video talking about the falling parachutist example, we showed that hey, we could solve a differential equation describing the velocity of the falling parachutist using calculus, and it gave us some exact solution that I'm denoting by this blue curve. And then I also showed how we could use a finite difference approximation for the derivative and come up with a numerical solution that looks something like these dots here. So the solution was only given at discrete points separated by some value delta t. And then in the next lecture we talked about the error, that there's actually error in between this approximation and the exact solution, and that error we denoted as the true error. That was equal to the true value minus our approximation. And then I also showed you how if we actually take this spacing and we chop it in half, so instead of having 1, 2, 3, 4 intervals, now we're going to have 8, so we chop each of these intervals in half. And we come up with a new delta t. So this is our new delta t value here, and it's equal to, I'll call it delta t prime, which is equal to our previous delta t over 2. If we did that, we actually found that our numerical solution fit much closer to the actual exact solution, and so the error, the true error, went down, got smaller. And so the question that I want to pose to you now is, if we cut the time step in half, how much does the error reduce? So if we cut the error, or if we cut the delta t in half, how much does the error reduce? And can we quantify it? So, can we quantify it? So those are the two questions we want to ask. And there's a mathematical tool known as the Taylor series that actually allows us to quantify the error in this numerical approximation to the differential equation. So that's what I'm going to introduce to you now, is the Taylor series, or Taylor's polynomial is another name that it's called, and Maclaurin series is a special case of the Taylor series, so you might have heard of those. Alright, so I'm actually just going to first draw a little picture here of a function. And so let's just say this is a function of x, and this is f of x, and maybe the function looks something like this. Okay, but let's say we actually don't know what the function looks like all we know is something about the function at this point right here. And we'll call this point xi. And xi is going to be our centering point for our Taylor polynomial, or our Taylor series. So xi is the Taylor series or Taylor polynomial centering point. And so what the Taylor series allows us to do is say take information about a function that we know at one point and use it to predict the value of the function at some other point. I'm going to call this other point xi plus 1. Okay, so let's say we want to know the value of the function here, but we don't know anything about the function except for at this previous point. So this is where the Taylor series can be helpful. So what I'm going to do actually is just write down the definition for the Taylor series. So the Taylor series says if we want to know if we want to come up with an estimate for this value, or actually even know it exactly, Taylor series says this point right here is exactly equal to, how do I want to write this? I'm actually going to write this, see this, I'm going to call this distance here h. This distance is h. So h is literally equal to xi plus 1 minus xi. So if I want to know the point of this function at xi plus h, which is the same thing as xi plus 1, then that is going to be equal to our function at xi plus the first derivative of the function, also evaluated at xi, times h, plus the second derivative of that function, so f double prime, evaluated at xi, times h squared, all over 2 factorial. And this continues for as many terms as we want to write down, infinitely following this pattern. So the next term is going to include the third derivative over 3 factorial, etc. But if we want to truncate it, we can kind of capture all the remaining terms in one final term, which we will call Rn. So however many terms we want to go out. So say we include all the way out to n terms, well, this Rn is going to capture that behavior. And so this is called the Taylor series of f centered at xi to predict that function at some value xi plus h. Now Rn here has a name, and it's called the Taylor remainder. And it's actually equal to the n plus 1th derivative of our function evaluated at some point psi times h to the n plus 1 power, all divided by n plus 1 factorial. Now, I'll explain more about this Taylor remainder in a moment. But right now, I want you to look at this and see that, okay, hey, we're trying this Taylor series right here is telling us what this point is equal to. It's equal to the value of itself evaluated at this point. So it's this point right here is f at xi, right? And you see all the function and its derivatives are all evaluated at this point right here, xi, the centering point. So I'm telling you that this function this value of the function right here can be written in terms of the function itself evaluated at some previous point, and also the function's derivative evaluated at that previous point. So how is this useful to us? Well, actually, before I kind of go into that, I want to explain to you a little bit more about each one of these terms. So first of all, if we just wanted to approximate our function, let's go back up here. Let's say we didn't know this function, but we wanted to figure out what it was at xi plus 1. So we don't know that it's equal here. Well, here we could look at this function and we could say, well, if it's not changing very much, we might guess that it's pretty close to what it used to be. And especially if this h value is small, we would guess that, hey, it's probably just equal to itself over here, f of xi. Now this is called the 0th order approximation. 0th order approximation. Now, if we knew information about this function's derivative, then we could say, hey, is the derivative large or small? And is it positive or negative? If it's, let's just assume it's positive. Actually, here the derivative is negative, so let's just say no, this is positive, sorry. So positive, so we might guess that, okay, if the derivative doesn't change between here and this point xi, then we might assume that we could just, hey, draw a line out from here, and the slope of this line represents the derivative here. We could use this as our next approximation. We call that a first order approximation. First order. Now second order, so you can see this is just the 0th order approximation. This is 0th order. This, when we include two terms, when we include information about the first derivative, this is a first order approximation. And if we include information of the second derivative, that's a second order approximation. We go out. So now that you kind of have an idea of what the different orders mean, so if I include one term, that's a first order approximation in the Taylor series. If I include two terms, it's a first order. If I include three terms, it's a second order, and so on. Now, again, how is this useful in regards to error? That's what we want to answer next. And so, what I want to do is show you how we can use this Taylor series, a truncated Taylor series, to come up with an approximation for the derivative, to come up with a finite difference approximation. So let's draw our velocity function for our falling parachutist. This is t, this is v sub t, and let's call this point ti, this point ti plus 1. The separation between these two is going to be delta t. Okay, and our velocity function here. Now, if we want to know the velocity's derivative at ti, let's say we know the velocity at this point and at this point. Now we want to come up with an approximation for the velocity here. Well, what we can do, what we did before, is I just wrote down a finite divided difference, but I'm going to show you how you can actually derive that from the Taylor series. So, what I'm actually going to do is I'm going to write down a Taylor series to predict what is the Taylor series for v at ti plus 1. Another way to write that would be v at ti plus delta t. Okay, that is going to be equal to v at ti, this is the Taylor series, plus v prime at ti times delta t plus v double prime at ti times delta t squared all over 2 factorial plus other terms. Okay, and so I'm just not going to write down the other terms, I'm just going to stop right here. And now what I can do actually is I can solve this equation right here. I can solve this equation right here for the derivative at ti, which is, I wanted an approximation for the derivative of v at ti, and so I'm going to solve this, get this, isolate this on one side of the equal sign. So if I do that, if I move these other terms over, v sub ti, then I'm going to have v prime at ti is going to be equal to v at ti plus 1 minus v sub ti minus v prime at ti, v double prime at ti over 2 factorial times delta t squared, right? And I'm going to have a delta t next to this v prime still. So this term has a delta t next to it. So now I just have to divide through by delta t. When I do that, I get v prime at ti is equal to v at ti plus 1 minus v at ti all divided by delta t minus v double prime at ti over 2 factorial times, now this just becomes delta t because we divided through by delta t. So what we can see here is this is what we actually used for our approximation to the derivative before. So this term right here and all the other terms that we cut off represent the error in this approximation to the derivative. So this is our approximation. This is our derivative approximation, and this, including all the terms that we cut off, represent the error in the approximation. So the interesting thing about this is, the second derivative of v evaluated at ti divided by 2 factorial. We don't know what that number is. It's just going to be some number, and we don't know how big or small it is. What we do know is we know how big delta t is. So another way that we could write this is v sub ti is equal to v sub ti plus 1 minus v sub ti all over delta t plus some function of delta t. So, and we know that it's going to scale as delta t, linear. It's not going to scale as delta t squared. So what this tells us is how the error changes when we change the size of delta t. So if I take and I use this approximation for the derivative, I can expect the error to scale as delta t. So what that means is if the error is proportional, see if I can write this, proportional to delta t, what happens when I cut the error in when I cut delta t in half? So if I cut delta t in half, I would expect the error to get cut in half as well. Now, what would happen if the error was proportional to delta t squared? What would happen now if I cut delta t in half? Well, if I gave a new delta t prime was equal to delta t over 2, and then I plug this in over here, what I'm going to get is now the error is going to go as the new delta t is we're going to have delta t over 2 squared, which is going to equal delta t squared over 4. So that means our error is going to be cut in 4. It's going to be reduced by a factor of 1/4. And correspondingly, if the error was proportional, so if our error was order delta t cubed, then we'd expect it to 1/8 the error when we cut the error in half, and so on. So the Taylor series here has given us a way to figure out the order of error. This is what we call the order of error with respect to delta t, or in more general terms, with respect to h. Remember earlier we talked about the Taylor series up here, and we were just talking about this step size in general we called h. So oftentimes in textbooks you'll see it with regards to h. Alright, so the Taylor remainder in general, it's the last thing I want to explain. The Taylor remainder, Rn, tells us how bad the error is. So remember, this was equal to f sub m plus 1, the nth plus 1 derivative evaluated at psi all times h to the n plus 1 power over n plus 1 factorial. So what this means is if I write a Taylor series f of xi plus h, and I only include the first two terms, so the 0th order approximation and the first order approximation, f prime at xi times h, that means our Taylor remainder is going to be R2, and that is going to be equal to R2 is going to equal f, actually this is how many terms? Yeah, we've included two terms, so actually I think this should be R1. Yeah, because we did first order, right? We went to first order. So this is 0th order, first order. So we did first order, so this is going to be n plus 1. That gives us the second derivative. So I'm just going to do prime at psi times h to the n plus 1, which is just going to be squared, over n plus 1 factorial, which is going to be 2 factorial. Now, the definition of psi is just that psi is said to be between xi and xi plus h. So all we know, all that we guarantee is that psi is somewhere in this interval where this is xi and this is xi plus 1 or xi plus h, where h is this distance here. Okay, this is our function. So that's the definition of the Taylor remainder. And so the Taylor remainder gives the order of error of our approximation. Alright, so just in summary, we showed that the Taylor series can be used to derive approximations for derivatives. These approximations are actually called finite difference approximations. Finite difference approximations. And we also showed that the Taylor series can be used to determine the order of error. The order of error in those approximations. Alright, that's going to be it for this video, and we'll see you in the next one.